In the profound quiet that settles after sunset, when the last echoes of the day have faded into the earth, the true nature of our world reveals itself. We are not on a closed stage, but adrift in an immensity so vast it defies the very language we use to describe it. Above us, a tapestry is unfurled, each point of light a sun, each sun a possible world, each faint smudge a congregation of billions more. It is a map of deep space and deep time, written in a code of photons that have journeyed for millennia to reach this precise moment, this glancing collision with the retina of a conscious observer. Among these ancient messengers, one appears with a distinctive hue, a subtle difference that to the casual glance might seem a mere quirk of atmosphere or optics. But this difference is the first whisper of a monumental truth. In the constellation of Orion, the hunter, perched upon his shoulder like a burning ember cast from a celestial forge, shines a star named Betelgeuse. Its light is the color of cooled iron, of autumn leaves, of a distant hearth fire. It is the color of transformation, of energy dissipating across a surface so vast it stretches the limits of plausibility. To look upon it is to look upon a clock, its hands poised at a minute to midnight, in a timekeeping system where the hours are measured in millions of years. This is not a permanent fixture. It is an event in slow motion, a promise of cosmic violence written in the peaceful language of a steady, rust-colored glow. The story of this star is the story of thresholds crossed and balances broken. It is a narrative of elemental alchemy, where the simple building blocks of the early universe are compressed and fused into the complex ingredients of planets and life. It is a meditation on scale, where the human lifespan is but a flicker against the billion-year cadence of stellar evolution. And it is a lesson in perspective, teaching us that our safe, blue world is a temporary haven in a galaxy that churns with both creative and destructive ferocity. Tonight, we begin not with the cataclysm to come, but with the silent, patient act of observation. We begin by tracing the path of that ancient light from its tumultuous origin across the desolate, beautiful gulf of interstellar space to the quiet of our own atmosphere. We will follow it backwards in time, unraveling the layers of its history, descending into the heart of the star itself to witness the physics of its impending demise. We will then cast our gaze outward again to understand the consequences of that demise for the galactic environment and for our own planetary home. We will confront the mysteries that still shroud our understanding, the companion that may share its orbit, the perplexing signals of its rotation, the cryptic rhythms of its pulsating heart. This is an exploration of the ultimate fate of matter, and in tracing that fate, we will inevitably trace our own lineage. For we are not separate from this drama, we are its product. The calcium in our bones, the iron in our blood, the very oxygen we breathe, were all forged in chambers of extreme pressure and heat within stars that lived and died long before our sun ignited. Betelgeuse is currently performing that same alchemy, and in its death throes, it will complete the process, scattering its enriched ashes into the void where they may one day coalesce into new worlds. So let us adjust our vision, not merely to see a point of light, but to perceive a process. Let us understand that the tranquility of the night sky is a magnificent illusion, a snapshot of processes so slow they seem static, and of events so distant their violence is reduced to gentle twinkling. Betelgeuse is our key to piercing that illusion. It is close enough to study in detail, yet far enough to pose no threat. It is a cosmic laboratory, a premonition, and a masterpiece of natural physics. Its story is one of fire, gravity, transformation, and legacy. It begins, as all great cosmic stories do, with a simple, almost imperceptible condensation in the dark. Long before the first human eyes looked up and recognized a hunter in the pattern of stars, before the myths of Osiris or the epic tales of Greek heroes were woven, the light from this particular region of space was already bathing the Earth. The photons that would one day be interpreted as Betelgeuse were streaming through a universe younger, denser, and more turbulent. They passed through epochs when our planet was a molten ball, when the first tentative molecules of life replicated in primordial seas, when dinosaurs ruled and fell, and when the ancestors of humanity first stood upright on the savannah and looked to the heavens with wonder. The human connection to the night sky is a tapestry woven from many threads. Practical necessity, spiritual yearning, and an insatiable curiosity. For nomadic peoples, the stars were a compass and a calendar. The reliable, cyclical appearance of constellations marked the seasons for planting and harvest, for migration and ceremony. Orion, one of the most prominent and recognizable patterns in both the northern and southern hemispheres, served as a universal celestial landmark. Its distinctive belt of 3 bright stars, its brilliant blue-white foot star Rigel, and its unmistakable reddish shoulder star provided a fixed geometry against which the wandering planets and the changing moon could be tracked. But beyond utility, these patterns became canvases for the human imagination. They were populated with gods and heroes, animals and artifacts, each culture projecting its own stories onto the indifferent sparkle of distant suns. The ancient Egyptians saw in Orion the figure of Osiris, the god of the afterlife, resurrection, and the Nile's fertile flood. His presence in the sky was a promise of cyclical renewal. The Greeks saw a mighty hunter, eternally pursuing the Pleiades across the firmament, a narrative of eternal desire. In Mesopotamia, it was the shepherd of Anu. To the aboriginal peoples of Australia, the stars of Orion's belt were 3 young men who pursued the 7 sisters of the Pleiades, a story encoded in songlines that crisscross the continent. And in that constellation, across these diverse mythologies, one star consistently stood apart for its color. While Rigel blazed with a fierce blue-white intensity, Betelgeuse glowed with a warmer, more somber tone. This color did not go unnoticed. It was often associated with blood, with war, with the hearth, with autumn, concepts linked to change, to maturity, to the closing of a cycle. The name Betelgeuse itself is a palimpsest of linguistic history, a testament to the journey of astronomical knowledge. It derives from the Arabic phrase Yad al-Jawza, which translates to the hand of the central one, al-Jawza being an old Arabic name for the constellation Orion. Through medieval Latin transliterations and scribal errors, Yad al-Jawza was misinterpreted. Yad al-Jawza was misread as Bide and combined with al-Jawza, leading to forms like Betelgeuse and eventually settling into the modern Betelgeuse. This etymological journey mirrors the astronomical one, an initial observation passed down and translated, sometimes corrupted, but gradually refined toward a more accurate understanding. That distinctive hue, so apparent even to the naked eye, is our first scientific clue to the star's true nature. The color of a star is not an aesthetic accident. It is a direct and precise indicator of its surface temperature, governed by the blackbody radiation laws of physics. A star like our Sun, with a surface temperature of approximately 5,770 Kelvin, emits light across a broad spectrum, but its peak emission falls in the yellow-green part of the visible range, which our eyes perceive as white. A hotter star, like Rigel, with a surface temperature soaring to around 12,000 Kelvin, peaks in the ultraviolet, but the steep fall-off of its radiation curve gives it a brilliant blue-white appearance in the visible spectrum. Betelgeuse, in stark contrast, is a cool giant. Its photosphere simmers at about 3,500 Kelvin. At this temperature, the peak of its emission is in the infrared, invisible to our eyes. The visible light we see is the long trailing tail of its energy output, dominated by red and orange wavelengths. This ruddy glow is the signature of a star that has undergone a profound internal metamorphosis. It is the visual manifestation of a body that has expanded to a grotesque and magnificent scale, its intrinsic energy now diluted across a surface area of unimaginable vastness. The color is a symptom of stellar old age, a warning light indicating that the stable, middle-aged equilibrium of hydrogen fusion has passed, and the star has entered its final, unstable, and grandiose phase. To comprehend the sheer physical scale of Betelgeuse requires a deliberate and disciplined effort of imagination, one that must systematically dismantle our terrestrial sense of proportion. Our Sun is the yardstick of our cosmic experience. It is a sphere of such grandeur that 109 Earths could be lined up across its diameter. Its mass, a staggering 1.99 times 10 to the power of 30 kilograms, constitutes 99.8% of all the matter in our solar system. Within its core, a perpetual thermonuclear reaction fuses 600 million tons of hydrogen into helium every second, releasing energy equivalent to the detonation of 100 billion 1 megaton nuclear bombs. This energy radiating outward takes 100,000 years to percolate through the dense radiative and convective zones, before bursting forth from the photosphere, then traveling for 8 minutes and 20 seconds across 150 million kilometers of void to illuminate and warm our world. This is the engine of our existence, and its scale is already numbing to contemplate. Yet this magnificent orb is utterly dwarfed by Betelgeuse. The term red supergiant is not merely a classification, it is a declaration of cosmic excess. Betelgeuse's radius is so immense that it is not conveniently expressed in solar radii, but in the very astronomical units we use to map our own planetary neighborhood. Current estimates, derived from advanced interferometric techniques, suggest its radius is approximately 900 times that of the Sun. To translate this into the geometry of our solar system, if Betelgeuse were placed at the center where our Sun resides, its tenuous outer atmosphere would extend well beyond the orbit of Mars. It would engulf the orbits of Mercury, Venus, Earth, and the asteroid belt, and its outer fringes would likely lap at the orbit of Jupiter over 778 million kilometers from the center. Within the volume defined by this monstrous sphere, one could fit approximately 1,400,000,000 suns. The mind recoils from such a number. It is not a comparison of objects, but of realms. Our entire star, with its retinue of planets, moons, and asteroids, would be a mere speck within the broiling, incandescent atmosphere of this Leviathan. This immensity, however, conceals a paradox of density. While its volume is beyond comprehension, its mass is estimated to be only between 10 and 20 times that of our Sun. All that matter is stretched so thin across the incredible volume that the average density of Betelgeuse is vanishingly small. It is less than a millionth of the density of Earth's air at sea level, and only about 1/10,000th of the density of the best laboratory vacuum we can create on Earth. Betelgeuse is not a solid incandescent ball. It is a titanic, shimmering bubble of rarefied plasma, a celestial furnace so diffuse that it verges on being a vacuum, a luminous cloud held in a precarious, temporary gravitational embrace. It is a star perpetually dissolving into space, its outer layers so weakly bound that powerful stellar winds stream from its surface, carrying away the mass of an entire Earth every few 100,000 years. This constant, prodigious mass loss is the star building its own funeral shroud, a circumstellar envelope of dust and gas that will one day be illuminated by the final blast. The existence of such a fragile, bloated behemoth is made possible by a delicate and dynamic balance, a cosmic tug-of-war that defines the life and death of every star. This balance is known as hydrostatic equilibrium. On one side of this equilibrium is the force of gravity, the most pervasive and patient architect in the universe. Gravity is an unrelenting, inward-pulling force that acts on every atom within the star, seeking to compress it into the smallest possible volume. It is a force that operates across the entire spectrum of scale, from the falling of an apple to the clustering of galaxies. Within a star, gravity's desire is total collapse. Opposing this crushing force is the outward pressure generated by nuclear fusion in the stellar core. In conditions of extreme temperature, exceeding 15 million Kelvin and immense density, atomic nuclei move with such ferocious energy that they can overcome their mutual electrostatic repulsion, a force known as the Coulomb barrier. When they come sufficiently close, the strong nuclear force, which operates only at subatomic distances, takes over and binds them together, forming a heavier nucleus. This fusion process results in a minute loss of mass, which, according to Einstein's monumental equation E=mc², is converted into a colossal amount of energy. For the majority of a star's life, this energy is produced by fusing hydrogen, the simplest and most abundant element, into helium. This is the proton-proton chain, or, in more massive stars, the carbon-nitrogen-oxygen cycle. The energy released creates immense radiation pressure and thermal pressure that pushes outward, precisely counterbalancing gravity's inward pull. The star achieves a stable, self-regulating state, a controlled thermonuclear explosion contained by its own gravity. This is the main sequence phase, and our Sun has been in this state for 4.6 billion years, with roughly 5 billion more to go. Stability, however, is contingent on a steady fuel supply. Hydrogen, though abundant, is not infinite. When the hydrogen in the core is finally exhausted, converted into an inert ball of helium, the graceful balance is shattered. The fusion engine sputters and stops. With no outward pressure from fresh energy generation, gravity gains the upper hand. The core, no longer supported, begins to contract under its own weight. This contraction is not a gentle settling, it is a violent compression that heats the core dramatically. As the core heats, it also heats the shell of unburned hydrogen that surrounds it. When this shell reaches the critical temperature for fusion, it ignites with a new ferocity. This shell burning is an act of desperation, a secondary energy source that produces far more power than the core's quiet hydrogen fusion ever did. This tremendous outpouring of energy from the shell does not stabilize the core. Instead, it pushes the outer layers of the star outward with irresistible force. The star expands, its surface area increasing by orders of magnitude. As it expands, the energy produced in the shell is spread over this vastly larger surface, causing the effective temperature of the photosphere to drop. The star cools and reddens. It has left the main sequence and entered the red giant phase. For a low-mass star, like our Sun, This is its final bloated state before it gently sheds its outer layers to form a planetary nebula, leaving behind a dense Earth-sized ember called a white dwarf. But for a star born with significantly greater mass, roughly 8 times the mass of the Sun or more, the story diverges onto a more extreme path. It becomes not merely a red giant, but a red supergiant. Betelgeuse, born with perhaps 15 to 20 solar masses, is such a star. Its current swollen immensity is a direct consequence of its core having exhausted its primary hydrogen fuel. It is no longer burning hydrogen in its center. It is a star in an advanced state of nuclear evolution, its interior structured like a cosmic onion, with layers of different elemental fusion surrounding an increasingly dense and complex core. This layered structure is a chronology of nuclear burning, each shell a testament to a fuel that was, and a ashes that became the fuel for the next. To venture imaginatively into the core of Betelgeuse is to journey into a realm of such extreme physics that familiar concepts of matter and energy dissolve. The core is a nested set of infernos, each hotter and denser than the last, each burning for a shorter duration. After hydrogen fusion ceased in the center, the helium core compressed and heated by gravity to around 100 million Kelvin ignited. Here, a remarkable process called the triple alpha reaction takes place. Helium nuclei, also known as alpha particles, fuse in pairs to form beryllium-8. Beryllium-8 is wildly unstable, with a lifetime of a mere 10 to the power of -19 seconds. Yet, in the dense, searing environment of the stellar core, a third alpha particle can collide with this fleeting beryllium-8 nucleus before it has a chance to decay, forging a stable nucleus of carbon-12. This process is the primary source of carbon in the universe. It is a delicate resonance, a fine-tuning of nuclear energy levels that allows this three-body reaction to proceed at a significant rate. Without this specific resonance, the universe would contain little carbon, and the rich chemistry of life would be impossible. As the helium fuel in the core is depleted, the cycle repeats: gravitational contraction, heating, and the ignition of the next available fuel. The carbon core, compressed further, reaches temperatures near 600 million Kelvin, igniting carbon fusion. This fusion can produce a variety of elements: neon, sodium, magnesium, and oxygen. Each fusion stage releases less net energy than the previous one, as the binding energy per nucleum increases, making the nuclei more stable and harder to fuse. Consequently, each stage burns at an exponentially faster rate. While hydrogen fusion may last for millions of years in a massive star, helium fusion lasts for perhaps 100,000 years. Carbon fusion might span 1,000 years, neon fusion a year, oxygen fusion a matter of months. The final act of silent nuclear creation is the fusion of silicon. At temperatures soaring above 2.7 billion Kelvin, silicon nuclei are shattered by photons in a process called photodisintegration, then reassembled through a complex series of reactions to form the iron group of elements, primarily iron 56 and nickel 56. This silicon burning phase is the star's last source of energy from fusion, and it may blaze with unimaginable fury for only a week. And here, at iron, the star's fate is irrevocably sealed. Iron 56 possesses the most tightly bound nucleus of all elements. Its nuclear binding energy per nucleum is at a maximum. This means that fusing iron into heavier elements does not release energy. It requires a massive input of energy. Similarly, splitting iron apart also consumes energy. Iron is nuclear ash. It is the endpoint of exothermic fusion in stellar cores. When the core of Betelgeuse accumulates a critical mass of this iron ash, nuclear fusion ceases entirely. The star's ultimate source of outward pressure winks out. The music of creation in its heart falls silent. What remains is a sphere of iron and nickel, roughly 1.4 times the mass of our entire Sun, compressed by its own immense gravity into a ball perhaps only a few thousand kilometers in diameter, the size of a small terrestrial planet like Earth, but with a density millions of times greater. Within this degenerate iron core, matter exists in a state unknown on Earth. The pressure is so astronomical that atoms are completely ionized. Electrons are stripped from their nuclei and exist as a degenerate Fermi gas. These electrons, governed by the Pauli exclusion principle of quantum mechanics, cannot occupy the same quantum state. As gravity tries to compress the core further, the electrons are forced into higher and higher energy states, generating an immense outward pressure known as electron degeneracy pressure. This pressure, born from the fundamental rules of quantum physics, becomes the last desperate support against total gravitational collapse. For a brief time, this quantum mechanical effect holds gravity at bay, but the core is not an isolated entity. It is a growing tomb. Above it, in the onion shell structure, the silicon burning shell continues its furious work, producing more iron and nickel that rains down onto the inert core, increasing its mass with every passing moment. This accretion pushes the core ever closer to a fundamental limit known as the Chandrasekhar limit, approximately 1.4 solar masses for a non-rotating core. It is a limit of stability for degenerate matter. When the core's mass teeters at this threshold, electron degeneracy pressure abruptly fails. It is a failure of quantum mechanics under the overwhelming force of gravity. In a cataclysm that unfolds in a few hundred milliseconds, the core collapses from thousands of kilometers to a mere 10 kilometers. The collapse is nearly unopposed, reaching velocities that are a significant fraction of the speed of light. In this unimaginable compression, electrons are forced into protons, converting them into neutrons and releasing a vast flood of neutrinos, elusive, nearly massless particles that barely interact with matter. The core is transformed into a neutron star, an object with the density of an atomic nucleus, where a teaspoon of material would weigh billions of tons. The collapse, however, does not end gently. The outer layers of the iron core, still rushing inward at relativistic speeds, suddenly encounter the newly formed, rigid surface of the neutron star. This is like a colossal stellar heart attack. The infalling material bounces off this ultra-dense boundary, creating a rebounding shockwave of stupendous energy. This shockwave is initially stalled by the continuing onslaught of material falling from the outer shells of the star, but it is revived by a crucial mechanism: the torrent of neutrinos. These neutrinos, carrying away 99% of the gravitational binding energy released in the collapse, are initially trapped in the dense core. As they diffuse outward over a few seconds, they deposit a fraction of their colossal energy into the stalled shock front, like a cosmic defibrillator. This neutrino heating reignites the shock, giving it the energy to blast outward through the still infalling outer layers of the star. This rebounding, neutrino-driven shock becomes a detonation wave that rips the entire star apart in a cataclysm known as a core collapse supernova. Specifically, a Type II supernova if the star had retained its hydrogen envelope, as Betelgeuse has. This is the fate that awaits Betelgeuse. The energy released is almost beyond human comprehension. In the span of a few seconds, The supernova emits more energy than our Sun will over its entire 10 billion year main sequence lifetime. For a brief period, it can outshine the combined light of every star in its host galaxy. Propagating at speeds up to 10% the speed of light, carries with it the newly synthesized heavy elements, the carbon, oxygen, neon, magnesium, silicon, sulfur, calcium, and iron, and through additional rapid neutron capture processes during the explosion itself. Elements heavier than iron like gold, silver, iodine, and uranium. This material is violently ejected into the interstellar medium. This is the ultimate act of cosmic alchemy. The death of a massive star is the birth of the periodic table's heaviest members. It is the source of the elements that form rocky planets, the minerals of Earth, the chemistry of oceans, and the very molecules of life. Every atom of oxygen we breathe, every atom of carbon in our bodies, every atom of iron in the hemoglobin of our blood, was forged in a star that lived and died before our Sun was born. We are, in the most literal and profound sense, stardust. Betelgeuse is currently in the process of creating these very elements, and in its final moment, it will complete the synthesis and scatter its legacy across its corner of the galaxy. This grand finale, however, is not an abstract, distant event. It is a physical phenomenon with a sphere of influence, a wave of destruction and creation that propagates through the galactic environment with measurable consequences. The immediate vicinity of a supernova is a place of utter annihilation. Any planet orbiting within a few light years would be subjected to a flash of ionizing radiation, gamma rays, X-rays, and extreme ultraviolet light, so intense it would vaporize surface rock, strip away planetary atmospheres molecule by molecule, and sterilize the surface down to a considerable depth. The kinetic energy of the expanding ejector, arriving hours to days later, would then sweep away any remaining physical structures, grinding worlds to dust. But as with any explosion, its ferocity diminishes with distance according to the inverse square law. The intensity of radiation or the density of ejector is inversely proportional to the square of the distance from the source. Double the distance and the effect is reduced to a quarter. Increase the distance tenfold and it becomes 100th. This simple physical law is our primary shield against cosmic violence. The critical question for us, inhabitants of a small fragile world orbiting a nondescript G-type star, is one of proximity. How close is too close for a supernova to pose an existential threat to the biosphere? To answer this, we must look not only forward to Betelgeuse's future explosion, but backward into the geological and paleontological history of our own planet. Earth, over its 4.5 billion year history, has not been an isolated island in a serene cosmic sea. It has been bathed in the light of countless supernovae in our galactic neighborhood. Our solar system resides in a region known as the local bubble, a vast cavity in the interstellar medium roughly 1,000 light-years across, filled with hot, tenuous, million-degree plasma. This bubble is not a primordial feature. It is a scar, a monument to past stellar violence. The prevailing astrophysical theory suggests this cavity was carved out by a series of perhaps 15 to 20 supernovae that detonated within a nearby stellar association, the Scorpius-Centaurus OB association, between 10 and 20 million years ago. These explosions, occurring at distances of a few hundred light-years, would have swept away the cooler, denser interstellar gas and compressed surrounding clouds, potentially triggering the gravitational collapse that led to the formation of new stars. Some astronomers posit that one such shockwave may have even played a role in triggering the collapse of the molecular cloud that gave birth to our own Sun and its stellar siblings roughly 4.6 billion years ago. We are, in a sense, children of a supernova-enriched and supernova-shaped environment. The very material from which our solar system condensed was laced with the radioactive ashes of earlier stellar generations. More direct and tangible evidence of nearby supernovae is embedded in the Earth itself, in the slow-turning pages of the geological record. On the ocean floor and within certain terrestrial rock layers, scientists have discovered anomalous concentrations of a rare radioactive isotope, iron-60. This isotope is pivotal because iron-60 has a half-life of 2.6 million years. It is not produced in significant quantities by natural processes on Earth. Its presence in crustal sediments is a definitive smoking gun signature of extraterrestrial origin. Iron-60 is forged in the final moments of a massive star's life, and during the supernova explosion itself, and it is ejected into space. Finding a layer of sediment enriched with iron-60 is like finding a distinct layer of ash from a specific, distant forest fire in a global sedimentary sequence. One prominent layer, identified in deep-sea ferromanganese crusts and sediments across the globe, is dated to approximately 2.6 million years ago, coinciding with the late Pliocene epoch. This period witnessed significant climatic shifts and a series of minor extinction events, particularly among marine mollusks. The implicated supernova is estimated to have been between 150 and 300 light-years away. At that distance, the direct physical blast and heat would have been negligible. However, the sustained bombardment of cosmic rays, high-energy atomic nuclei, primarily protons, accelerated to near-light speeds by the expanding supernova shockwave, could have had a subtle but significant impact on Earth's climate and biosphere. An increased flux of cosmic rays penetrating our atmosphere would have ionized molecules, potentially leading to the formation of cloud condensation nuclei. This could have increased global cloud cover, reflecting more sunlight back into space and contributing to a cooling trend. Furthermore, the enhanced radiation dosage at the planet's surface and in the upper layers of the ocean could have acted as a mutagenic stressor on life, possibly influencing the course of evolution. While not an apocalyptic event, it stands as a testament to the interconnectedness of cosmic and terrestrial phenomena, a distant stellar death leaving its faint imprint in the rocks and the evolutionary history of our world. A more controversial and dramatic hypothesis pushes this connection further into the realm of geologically recent history. The Younger Dryas period, roughly 12,900 years ago, marks a sudden and dramatic return to near-glacial conditions in the Northern Hemisphere, a chilling reversal that lasted over 1,000 years, just as the Earth was emerging from the last ice age. This period coincides with the extinction of many large mammalian megafauna, including the woolly mammoth, mastodon, and saber-toothed cat in North America, and a significant decline in Paleo-Indian cultures. Some researchers have proposed that a fragment of a supernova ejecta, a dense knot of material from a relatively nearby explosion, could have struck the Earth's atmosphere or surface. The resulting energy release, akin to a large airburst or impact, could have triggered continent-wide wildfires, injected vast quantities of soot and dust into the upper atmosphere, and precipitated a rapid impact winter. Evidence cited includes sediment layers from that time containing microscopic magnetic spherules, nanodiamonds, and elevated levels of other isotopes like plutonium-244. This hypothesis, often called the Younger Dryas impact hypothesis, remains fiercely debated within the scientific community. Many of the purported impact markers have been challenged, and alternative explanations for the climate shift, such as changes in ocean circulation patterns, are widely accepted. Nevertheless, the very existence of the debate underscores a profound and sobering point. Our planet is not an isolated, self-contained system. It exists within a dynamic, flowing, and occasionally violent galactic ecosystem. The history of life on Earth, its triumphs, its extinctions, its evolutionary pathways, has been written not only by plate tectonics, volcanism, and biological competition, but also, in part, by events occurring light years away in the turbulent hearts of dying stars. The universe writes its history in many layers, and terrestrial geology is but one page in a much larger cosmic chronicle. This historical and geological perspective allows us to calibrate the true threat posed by Betelgeuse with empirical rigor. Life on Earth has persisted for nearly 4 billion years, through countless supernovae that have undoubtedly occurred much closer to our solar system than Betelgeuse is today. The fact that life not only survived, but evolved into the breathtaking complexity and conscious awareness that allows us to ponder these very questions tells us that supernovae are not an existential threat to a planet at our typical galactic distance. They are a regional phenomenon with a kill zone that is cosmically small. Sophisticated astrobiological models suggest that a core collapse supernovae would need to occur within approximately 25 to 50 light-years of Earth to pose a direct, catastrophic danger to the complex biosphere. At that perilously close range, the initial flash of gamma rays and X-rays, followed by a sustained bombardment of cosmic rays over centuries, would likely devastate the planet's protective ozone layer for years. This would allow lethal levels of ultraviolet radiation from our own Sun to penetrate to the surface, causing widespread damage to DNA in terrestrial and shallow marine organisms. The collapse of phytoplankton populations, which form the base of the marine food web and produce a significant portion of the planet's oxygen, could trigger a cascade of extinctions and potentially alter the atmospheric composition. Betelgeuse, at a distance of approximately 650 light-years, is 26 times farther than the conservative end of this danger zone. The inverse square law is our robust and reliable shield. The intensity of harmful radiation at our distance would be reduced by a factor of nearly 700. While the visual spectacle would be unparalleled in human history, it would be biologically harmless. The event would deliver a minuscule, undetectable increase in background radiation, far less than a typical medical X-ray or a flight across the Atlantic. Our safety is not a matter of luck, but a consequence of the vast insulating scales of interstellar space. We can extend this survey of our stellar neighborhood to ask a broader question. Are there other, closer candidates poised for such a dramatic end? The Milky Way galaxy contains hundreds of billions of stars, but massive, short-lived stars like Betelgeuse are rare, constituting less than 1% of the stellar population. Their very brilliance makes them relatively easy to catalogue within a few thousand light-years. Within 300 light-years of Earth, the only other classic red supergiant of comparable stature is Antares, the fiery heart of the constellation Scorpius, which lies at a distance of about 550 light-years. Other potential supernova progenitors include white dwarfs in binary systems that can accrete matter until they reach the Chandrasekhar limit and undergo thermonuclear disruption in a type I supernova. These systems are fainter and more difficult to census comprehensively. However, the European Space Agency's Gaia mission, a revolutionary astrometric observatory, is transforming our stellar cartography. By precisely measuring the positions, distances, and motions of over 1 billion stars, Gaia has enabled a much more complete inventory of local white dwarfs. Detailed analysis of this immense dataset suggests that while thousands of these stellar remnants populate our galactic vicinity, none are currently in binary configurations or possess mass characteristics that would indicate an imminent detonation within the next several 100,000 years. For the foreseeable future, from a supernova perspective, Earth occupies a quiet, sheltered backwater in the Orion spur of the Milky Way galaxy. The existential threats to our biosphere are far more likely to be endogenous: volcanic supereruptions, asteroid impacts, anthropogenic climate change, or self-inflicted technological hazards. The cosmos provides a backdrop of majestic violence, but for now, it is a spectacle, not a sword of Damocles. This assurance of safety grants us a privileged and unique position, that of the prepared spectator. When Betelgeuse finally does explode, it will present the ultimate cosmic spectacle, a front-row seat to one of the universe's most energetic and transformative processes. It will be a scientific bonanza of unprecedented scale and import. For the first time in the history of modern astronomy, we will be able to observe a nearby, well-studied, and seemingly ordinary red supergiant undergo core collapse, with the full arsenal of 21st century technology. The event will be a multi-messenger astronomical revolution. The first signal to arrive will be the neutrino pulse, a flood of these ghostly particles that will pass through the Earth hours before the first light from the shock breakout reaches us. Gigantic underground detectors like Super Kamiokande in Japan, the Ice Cube Neutrino Observatory at the South Pole, and the upcoming Deep Underground Neutrino Experiment will register a dramatic spike, a direct telegram from the heart of the collapsing core, providing instantaneous information about the dynamics of neutron star formation. Minutes to hours later, space-based gamma-ray and X-ray observatories will detect the shock wave breaking through the star's photosphere, a sudden, intense flash of high-energy radiation. Then the optical light will begin to rise. Ground-based telescopes across the globe and orbiting observatories like the Hubble Space Telescope and the James Webb Space Telescope will track the light curve as it ascends to peak brightness. Betelgeuse will transform from a point of light into a resolvable disk, then into an expanding fireball. Its brightness will increase until, at its peak, it will shine with the intensity of a half moon or even a full moon, visible in broad daylight as a brilliant, piercing white point next to the sun. It will cast faint, surreal shadows at night. For a period of weeks or months, it will be the brightest star in the history of human civilization, a second sun in the night sky. Its color will change as the expanding ejecta cool, shifting from blue-white to yellow and then red. Simultaneously, gravitational wave observatories like LIGO and Virgo may detect the ripples in spacetime produced by the asymmetric collapse of the core or the vibrations of the newly born neutron star, providing a completely independent channel of information about the cataclysm. Radio telescopes will map the expanding shell of debris as it plows into the circumstellar material shed during the star's red supergiant phase, creating a brilliant, evolving nebula. Every moment, across every wavelength and particle channel, will be a precious data point, refining and perhaps revolutionizing our models of stellar death, nucleosynthesis, and the birth of compact objects. But beyond the raw scientific harvest, there is a profound cultural, philosophical, and human dimension to this anticipated event. For a brief period, the supernova would become a central fact of human existence. It would be recorded in every culture, in every language, by every person with access to the sky. It would inspire awe, fear, poetry, art, and new mythologies. It would be a subject of news broadcasts, social media, scientific papers, and religious sermons. It would be a unifying event for humanity, a shared experience written across the heavens, reminding us of our common vulnerability and curiosity on this small planet. It would force a collective contemplation of our place in the cosmos, of the impermanence of even the seemingly permanent fixtures of our sky. It would be a global, teachable moment about astrophysics on a scale never before possible. And then, over the ensuing years and decades, the glow would fade. The ejected nebula would expand and dim, becoming a faint, colorful cloud visible through telescopes, a new celestial object, the remnant of Betelgeuse. At its heart, the crushed remnant of the star's core would remain. If the core mass is between about 1.4 and 2.5 solar masses, it will be a neutron star. If it is spinning rapidly and has a strong magnetic field, it may be a pulsar, beaming lighthouse-like pulses of radio waves across the galaxy. If the core is more massive, perhaps above 2.5 solar masses, even neutron degeneracy pressure will fail, and it will collapse directly into a black hole, a point of infinite density shrouded by an event horizon. The constellation Orion will be forever altered. Its familiar silhouette, known for tens of thousands of years, will be missing its amber shoulder jewel. For centuries, the asterism will appear lopsided, a silent reminder of the transience of the cosmic landscape. The central, tantalizing mystery, then, is not if, but when. The timer is ticking deep within the iron-forging core of Betelgeuse, but its face is obscured by hundreds of millions of kilometers of turbulent plasma. Soon, in astronomical terms, is a frustratingly flexible word. It could mean tomorrow. It could mean 100,000 years from now. The star itself holds the answer, encoded in its intricate structure and its complex, multi-rhythmic behavior. To decode this, astronomers have turned Betelgeuse into one of the most intensely studied stars in the sky, second only to our Sun. Its immense apparent size, though still a minuscule fraction of a degree, makes it a prime target for high angular resolution techniques. The most powerful of these is optical and infrared interferometry, where light from multiple telescopes, separated by hundreds of meters, is combined to achieve the resolving power of a single instrument as large as the distance between them. Through facilities like the Very Large Telescope Interferometer and the CHARO array, we have obtained remarkable, though pixelated, images of Betelgeuse's disk. They reveal not a smooth, placid sphere, but a dynamic, seething, and asymmetric cauldron. Massive convection cells, each larger than the orbit of Earth, churn the photosphere. These are bubbles of hot plasma rising from the deep interior, cooling at the surface and sinking back down in a continuous, energetic cycle. The star's brightness is not constant. It is a variable star, rhythmically expanding and contracting. These pulsations are the star's heavy, labored breaths as it approaches its end. Several overlapping periodicities have been identified. A primary cycle of about 420 days is well established, linked to the fundamental radial pulsation of the star as a whole, its entire envelope rhythmically swelling and shrinking. There are shorter cycles of perhaps 180 to 200 days, and longer, more perplexing ones, most notably a cycle of approximately 2,170 days, nearly 6 Earth years. Determining which of these is the true fundamental mode, the key heartbeat most directly tied to the star's internal structure, mass, and evolutionary state, is crucial for refining estimates of its remaining lifetime. Stellar evolution models suggest that the longer the fundamental pulsation period, the more evolved and closer to core collapse the star is believed to be. The 6-year cycle, if it were the fundamental mode, would imply a star very near the end. But the interpretation of these rhythms is fraught with complexity. This scientific scrutiny was catapulted from the realm of specialized journals into global public consciousness by a dramatic event dubbed the Great Dimming of late 2019 and early 2020. Over a period of months, Betelgeuse faded dramatically, losing nearly 2/3 of its normal luminosity, dipping from its typical position among the top 10 brightest stars to well outside the top 20. For a brief, exhilarating moment, speculation ran wild across both the astronomical community and the public. Was this the pre-collapse dimming predicted by some theoretical models? Was the supernova imminent? The global astronomical community mobilized an unprecedented observational campaign. Critical insights came from the Hubble Space Telescope. Its observations from before and during the dimming revealed that in the months preceding the event, the star had ejected a massive, localized plume of hot plasma from its southern hemisphere. This material, upon traveling away from the star, cooled and condensed into a vast cloud of dust, essentially carbon soot. This cloud, passing between Betelgeuse and Earth, acted as a cosmic veil, obscuring our view of a large portion of the star's luminous surface. By April 2020, the star had returned to its normal brightness as the dust cloud either dispersed or moved out of our line of sight. The Great Dimming was not a death rattle from the core, but a spectacular stellar sneeze, a colossal example of the episodic mass loss that is characteristic of red supergiants in their final, unstable stages. Betelgeuse is shedding its outer layers at a prodigious and variable rate, building its own funeral shroud. This ejected material will form the circumstellar medium that the future supernova shockwave will later plow into, lighting it up and creating the brilliant, structured nebula we will observe for millennia to come. The event was a powerful reminder of the star's active and messy death throes, a preview of the mass loss that will eventually strip it down to its bare, explosive core. The intense, focused scrutiny on Betelgeuse during the Great Dimming, however, yielded an unexpected and fascinating secondary discovery. One that may solve a century-old mystery and profoundly refine our understanding of the star's dynamics. For decades, astute astronomers had harbored suspicions that Betelgeuse might not be alone. Subtle, periodic irregularities in its proper motion through space and certain persistent features in its complex spectrum hinted at the gravitational tug of an unseen companion star. But proving its existence was extraordinarily difficult. The star's own violent pulsations, its churning convective surface, and its massive stellar winds created a noisy, chaotic signal that could easily mask the subtle periodic wobble induced by an orbiting partner. In the wake of the dimming event, two independent research teams, armed with fresh motivation and decades of accumulated radial velocity data, which measures the star's slight motion toward and away from us by the Doppler shift in its spectral lines, reanalyzed Betelgeuse's behavior with sophisticated new techniques. They both converged on the same compelling conclusion. The long 2,170-day cycle, the perplexing 6-year rhythm, was best explained not by an internal pulsation, but by the gravitational influence of a binary companion. As this companion, informally nicknamed, though not yet formally confirmed, orbits the primary, it pulls Betelgeuse back and forth in a slow, stately dance, causing a slight periodic Doppler shift in its light. The associated dimming at the same period could be due to partial eclipses if the orbit is viewed somewhat edge-on, or more likely to tidal interactions that enhance mass loss from Betelgeuse's immense atmosphere at specific points in the orbital phase, perhaps leading to increased dust production. The hunt for a direct image, for a visual confirmation of this elusive partner, was immediately intensified. Using the powerful Gemini North telescope on Mauna Kea in Hawaii, equipped with advanced adaptive optics to counteract atmospheric blurring and a sensitive speckle imaging camera, astronomers pointed at Betelgeuse at a time when the hypothetical companion was predicted to be at its greatest angular separation from the blinding primary. And there, at the very bleeding edge of the instrument's resolution and contrast capability, was a faint, persistent smudge of light. The candidate companion is exceedingly dim, perhaps 10,000 times fainter than Betelgeuse itself in the observed wavelength, and it orbits at a projected distance roughly comparable to the distance between our Sun and Saturn. Its mass is estimated to be around that of our Sun, a modest star utterly dominated by its colossal partner. If confirmed, and future observations, particularly around the next predicted maximum separation in the year 2027, will seek to solidify the detection, this discovery reshapes the entire narrative of Betelgeuse's final years. It means the long 6-year cycle is not the fundamental pulsation mode after all. Removing this period from the internal calculus of the star's evolution likely pushes the estimated time to core collapse further into the future, perhaps by a significant margin, dashing the hopes of those who dream of witnessing the supernova within our lifetimes. It also introduces a dramatic and poignant subplot to the stellar saga. The companion star, designated for scientific purposes, orbits deep within the extended tenuous outer envelope of the red supergiant. It is a world perpetually shrouded in a crimson haze of stellar wind, bathed in the infrared glow of its gigantic neighbor. Its orbit may be decaying due to dynamical friction with the sparse outer layers of Betelgeuse. And when Betelgeuse finally explodes, this companion will be perilously close to ground zero. It may be stripped of its own outer layers by the blast, violently perturbed into a new hyperbolic trajectory, flung out of the system as a runaway star, or even partially or wholly consumed in the expanding fireball. Its fate is a stark reminder of the collateral damage in cosmic events, a silent witness to a catastrophe of its own making, gravitationally bound to its destroyer. Another profound mystery surrounding Betelgeuse involves not its oscillations or its companion, but its rotation. Measuring the spin of a distant, blurry and turbulent star is a formidable challenge. It is achieved through a technique called Doppler imaging, applying the same shift principle across the resolved disk. By meticulously mapping the subtle red and blue shifts across the face of the star, the side rotating toward us is blue shifted. The side rotating away is red shifted. Astronomers can deduce the rotational velocity at the equator. Data from the Atacama Large Millimeter Submillimeter Array, a powerful radio interferometer in Chile, suggested something astonishing. Betelgeuse appears to be spinning at a breakneck speed of about 5 kilometers per second at its surface. This finding is profoundly puzzling and challenges a fundamental law of physics, the conservation of angular momentum. As a star expands into a red supergiant, its moment of inertia increases dramatically, just as a spinning ice skater slows when they extend their arms. If our Sun, rotating at about 2 kilometers per second at its equator, were magically expanded to the size of Betelgeuse, its rotation speed would drop to a barely perceptible few meters per second due to the conservation of its angular momentum. For Betelgeuse to be spinning at 5 kilometers per second, it would have needed to be born with an impossibly high initial spin, far greater than any known massive star, or it must have gained angular momentum later in life. One compelling, dramatic hypothesis is stellar cannibalism. The idea is that Betelgeuse may have once been part of a closer binary system with a more massive companion. As the more massive star evolved faster and expanded, mass transfer could have occurred, or perhaps the two stars even merged. The transfer of mass and, crucially, orbital angular momentum could have spun up the outer layers of the star that became Betelgeuse to the observed velocity. This would be a dramatic history, a story of cosmic consumption written in its present-day whirl, a hidden chapter of violence preceding the final act. Yet, the universe often favors the simplest explanation that fits all data, and a recent, elegant challenge has been posed to the fast rotation interpretation. A collaborative team of researchers from Europe and China proposed that the smooth Doppler gradient observed by ALMA might not be from bulk rotation at all, but a brilliant and complex illusion. The surface of Betelgeuse, as we know from interferometric images, is not smooth. It is a maelstrom of giant convective cells, each hundreds of millions of kilometers across, rising and falling at speeds up to 30 kilometers per second. These cells create their own localized patches of redshift and blueshift, a chaotic, bubbling mosaic of fluid motion. When such a complex, high-contrast pattern is observed through a telescope with finite resolution, the fine details are blurred together. In their sophisticated three-dimensional computer simulations of red supergiant convection, the team found that this blurring of a chaotic, turbulent surface can, about 90% of the time, produce an integrated spectral line profile and a low-resolution Doppler map that looks, for all the world, like a smooth, clean gradient of rotation. The apparent spin we think we see may simply be the superimposed statistical average of countless giant plasma bubbles boiling across the face of a star that is, in reality, turning very slowly or perhaps even differentially rotating in a more complex manner. This hypothesis does not require exotic scenarios of stellar mergers. It suggests that the signature of rotation is mimicked by the collective behavior of convection. It awaits rigorous testing with even higher resolution observations, perhaps from next-generation optical interferometers with more telescopes, or from the keen infrared eye of the James Webb Space Telescope studying specific spectral lines. It is a humbling reminder of the inherent challenges of interpreting data from the cosmic frontier, where what we perceive is always a filtered, processed, and often deceptive version of a profoundly complex reality. Our instruments show us a shadow of the truth, and it is the task of science to discern the shape of the object casting that shadow. So, we are left with a portrait of Betelgeuse that is rich, detailed, vibrant with discovery, and yet still profoundly enigmatic. It is a star in its final, unstable era, a titan shedding its skin, pulsating with multiple, overlapping rhythms, possibly dancing in a gravitational embrace with a doomed companion, and presenting us with tantalizing puzzles of its internal dynamics and rotational state. Every new observation, from the dimming event to the candidate companion to the convective simulations, adds a brushstroke, refines a line, or changes the hue of our understanding. But the complete picture of its imminent death remains unfinished, the final brushstroke withheld. The countdown is real, governed by the immutable physics of nuclear fusion and quantum degeneracy. The clock is hidden deep within its iron-forging core, behind veils of silicon, oxygen, neon, carbon, and helium. Our safety is assured by the vastness of space. Our curiosity is boundless, driven by the desire to comprehend the machinery of the universe. To watch Betelgeuse is to watch a masterpiece of stellar evolution in its final, most dramatic and expressionist brushstrokes. It is to understand viscerally that the cosmos is not a static backdrop, a painted ceiling for our earthly drama, but a living, evolving, and sometimes violently changing entity. The very processes that will ultimately destroy Betelgeuse, gravity's relentless crush and the failure of nuclear fire, are the same processes that over billions of years and across generations of stars created the essential elements of our planet and the chemistry of our biology. In its impending death, we are reminded of our own cosmic lineage, our indebtedness to stars that lived and died long ago. The star that will one day blaze with the light of 1 billion suns is for now a steady, ruddy point of light in our winter sky, a promise written in fire, a future spectacle, and a profound teacher. Its eventual detonation will be a fleeting, brilliant punctuation mark in the long, slow sentence of galactic history. But for a brief, singular moment in human history, it will command the attention of every conscious eye on Earth, a shared reminder of the awesome, beautiful, and terrifying power of the universe we inhabit. It connects our humble earthly perspective, measured in decades, to the grand billion-year cycles of stellar life and death. It is a bridge between human-scale time and cosmic deep time. The narrative of a star like Betelgeuse, however, extends far beyond the momentary flash of its cataclysmic end. The supernova event, while the spectacular climax, is merely the explosive beginning of its posthumous legacy. The ejected material, now racing outward at thousands of kilometers per second, will continue to expand for tens of thousands of years, gradually cooling and mixing with the surrounding interstellar medium. This enriched cloud, a nebula initially glowing from the radioactive decay of nickel-56 and cobalt-56, and later from the shock heating as it plows into pre-existing circumstellar material, will become a fertile nursery for future cosmic cycles. The heavier elements, the oxygen, carbon, silicon, iron, and traces of gold, silver, and uranium will be incorporated into dust grains. The shock wave from the explosion itself will propagate outward, compressing nearby clouds of molecular hydrogen and other gases. This compression can trigger gravitational instability, causing pockets within these clouds to collapse under their own weight. Within these collapsing pockets, new stars will be born, and around these new stars, accretion disks will form, and from the dust and gas in these disks, rocky planets may coalesce. Those planets will be built from material that was once part of Betelgeuse's outer layers. On some of those distant future worlds, in billions of years, conditions may allow for chemistry complex enough to give rise to self-replicating molecules and perhaps to life. And that life, should it evolve consciousness, may one day look up at its own night sky and with instruments detect the expanding remnant of the supernova that helped forge its world. In this way, the death of Betelgeuse is not an end, but a transformation, a glorious and necessary recycling of matter on a galactic scale. The iron in our blood, the calcium in our bones, the phosphorus in our DNA, all were forged in stellar furnaces and scattered by supernovae that exploded billions of years before our Sun was a glimmer in a molecular cloud. Betelgeuse is currently contributing to this ongoing majestic cycle of cosmic renewal. Its explosion will seed its corner of the Orion arm with the heavy elements, the very raw materials for future worlds and potentially for future life and consciousness. We are witnesses from a fortunate distance to a slow-motion act of creation that operates on timescales that dwarf all of human history, a process that turns destruction into the seeds of new beginnings. This perspective inevitably invites a deep contemplation of the nature of time itself and of our place within its flow. The light from Betelgeuse that we see tonight left the star's photosphere around the year 1374 during the late Middle Ages on Earth. We are observing it not as it is, but as it was over 6 centuries ago. If it exploded at this very moment, we would remain blissfully unaware for 650 years, the news traveling toward us at the finite, unbreakable speed of light. Our view is a haunting echo of the past. Conversely, any hypothetical observer on a planet orbiting Betelgeuse, a physical impossibility given the star's evolution, but a useful thought experiment, would see our Sun as it was in the 14th century. They would see light that left Earth when the Black Death was sweeping through Europe, when the Ming dynasty was founded in China, when the Renaissance was just beginning to stir in Italy. We are separated not only by a gulf of space, but by a canyon of time. This is the fundamental, poignant condition of astronomy and cosmology. We are always archaeologists of the present, deciphering ancient light. The Betelgeuse we study so meticulously is a historical artifact. Its current activity, its great dimming, its convective turmoil, all are messages from an epoch when human civilization was emerging from a period of upheaval and looking toward a new age of discovery. This inherent time lag adds a layer of profound irony to our urgent search for signs of imminent explosion. We are scrutinizing a portrait of a star painted centuries ago, looking for clues about a future event whose trigger may have already been pulled, a verdict already rendered in the core, its news still in transit, traveling toward us at the finite speed of causality. We are studying the past to predict the future of an object whose present is forever hidden from us. The ongoing study of Betelgeuse also forces us to confront the very limits of our knowledge and the essential nature of scientific inquiry. Despite the wealth of data from photometry, spectroscopy, interferometry, and polarimetry, key questions remain stubbornly unanswered, their answers hidden within the star's turbulent heart. What is the precise mass of Betelgeuse? This single parameter is perhaps the most critical, as it determines not only its remaining lifetime, but the ultimate fate of its core. Will the collapse halt at the neutron star stage or continue into a black hole? Current estimates, based on evolutionary models and binary interactions, range from 10 to 20 solar masses, an uncertainty factor of 2 that translates into vast differences in core composition and timescale. What is the exact three-dimensional structure of its inner nuclear burning shells? How asymmetric is its convective envelope? How asymmetric will the ultimate collapse and explosion be? The neutrino pulse and the gravitational wave signal will carry direct, unadulterated information about the dynamics of the core collapse, dynamics that are currently the domain of sophisticated but still approximate multidimensional computer simulations that must account for magnetic fields, rotation, and neutrino transport. Betelgeuse represents a living cosmic laboratory where theory meets observation in real time, and where each new anomaly, the great dimming, the binary hypothesis, the rotation mystery, drives the refinement of models, the questioning of assumptions, and the development of new techniques. Science does not proceed in a neat, linear path from ignorance to certainty. It advances through confusion, debate, competing interpretations, false leads, and the slow, painstaking, collective accumulation of evidence that eventually, and often grudgingly, tilts the scale toward one narrative over another. The story of Betelgeuse is being written in real time through this very messy, gloriously human process. It is a testament to our persistent drive to understand, to decode the universe, even when the universe presents us with a puzzle as complex and dynamic as a dying supergiant. On a deeper human level, the anticipation of Betelgeuse's supernova touches something archetypal within our psyche. We are drawn to the spectacle of destruction, yes, but also to the sublime, an aesthetic and philosophical experience that mixes awe, terror, and a sense of overwhelming, transcendent scale. A supernova visible in daylight is the very definition of the sublime. It represents a force of nature so far beyond human control, so far beyond our everyday experience, that it both humbles and exalts us. It pulls our gaze away from our terrestrial concerns, our conflicts, our ephemeral worries, and fixes it upon the cosmos and its grand, indifferent laws. In a world often fragmented by parochial differences, by borders and ideologies, the idea of a celestial event that would be seen simultaneously by every human being on the planet, regardless of nationality, creed, culture, or social status, is a powerful unifying thought. It is a reminder of our shared existence on a pale blue dot, under the same sky, subject to the same universal physics. For a few weeks or months, our mythologies, our art, our conversations, our very sense of the world would be shaped by a point of light in Orion. It would become a cultural touchstone for generations, referenced in literature, film, and music, a shared memory for all of humanity. It would be a global moment of collective looking up. And then, as all things must, the spectacle would fade. The light curve would decay, following the radioactive decay of cobalt-56 into stable iron-56. The nebula would expand, its surface brightness diminishing, becoming a challenging target for amateur telescopes. Then a target only for professional instruments, and eventually merging into the general glow of the interstellar medium. Orion's shoulder would remain dark for centuries, a missing piece in a familiar puzzle, until perhaps the light from the glowing nebula itself, energized by the shockwave interacting with older ejecta, creates a new, fainter, and more diffuse smudge of light. The neutron star remnant, if one is formed and if it is a pulsar with its beam pointing toward Earth, might be discovered as a faint, rapid radio beacon, a faint, precise heartbeat marking the grave of the giant. Life on Earth would go on, physically unaffected but potentially changed in its perspective. We would have witnessed, for the first time in all of recorded human history, the death of a familiar, named star. We would have concrete, visceral proof of the impermanence of the heavens, a concept understood intellectually since the time of the ancient philosophers, but never before demonstrated so vividly on a human timescale. The constellations, those seemingly eternal patterns, would be revealed as transient arrangements, snapshots in a slow cosmic dance that spans millions of years. Our own sun's future fate would feel more immediate, more real. We would have lived through a cosmic event that connected us directly to the life cycle of the galaxy. As we bring this contemplation to a close, we return to the present moment, to the quiet, fundamental act of looking up on a clear winter evening. Betelgeuse shines steadily, its distinctive red light, a testament to its great age, its immense size, and its feverish internal struggle. It is a beacon of stellar evolution, a sentinel standing on the brink between being and transformation. The questions of when and exactly how continue to drive the engines of scientific exploration, fueling proposals for new telescopes, new observational campaigns, and more powerful simulations. The mysteries of its possible companion, its true rotational state, and the precise interplay of its pulsation modes remain active and exciting frontiers of astrophysical research. But beyond the charts, the graphs, and the data points, Betelgeuse serves as a permanent, luminous symbol of a dynamic and evolving universe. It reminds us, every time we see it, that we are part of a story much larger than our own brief narratives, a story of gravity and nuclear fire, of creation forged in destruction, of seeds sown in stellar explosions that may, over incomprehensible spans of time, blossom into new worlds and perhaps new life. Its eventual supernova will be a brilliant, unmistakable full stop in one chapter of that grand story and the opening sentence of the next. The nebula will be its lasting monument, and the neutron star or black hole its silent tombstone. Until that day comes, whether it is tomorrow or in 100 millennia, we watch. We measure its light. We analyze its spectrum. We map its surface. We learn from it. We marvel at the precarious, magnificent giant whose light has traveled for centuries across the desolate beauty of interstellar space to reach our eyes, carrying with it the encoded tale of its own impending and glorious end. It is a reminder that the night sky we often take for granted is not a static painting, but a living, breathing narrative written in the language of physics. A narrative of birth, life, death, and rebirth on a scale that both dwarfs and encompasses us. We are here for a brief and fortunate moment in cosmic history to read that narrative, to decipher its symbols, and to feel a connection to the processes that gave us form. So the next time you find yourself beneath a clear, dark night sky, perhaps far from the glare of city lights, seek out the constellation of Orion. It is a universal landmark, visible across much of the globe. Find the 3 bright stars of his belt, aligned in a neat celestial row. Then let your gaze drift upward and to the left. There you will find it, that unmistakable, warm, orange-red point of light, Betelgeuse. Take a moment. Consider the reality of what you are seeing. You are not looking at a mere pinpoint. You are looking at a sphere of tenuous, raging plasma, nearly 1,000 times the diameter of our Sun, a sphere so large it could engulf the inner solar system. You are seeing a star in the final tumultuous centuries or millennia of its existence, a star whose core is a layered onion of nuclear ash, building toward an inevitable collapse. Feel the distance, 650 years. The light now entering your eye left the star around the time the Ottoman Empire was rising, before the voyage of Columbus, before the scientific revolution. Contemplate the future, the brilliant, harmless spectacle that awaits your descendants, perhaps in 100 years, perhaps in 100,000. It is a future event that is already inscribed in the star's present state, a causality chain that is currently unwinding in the slow-motion physics of stellar interiors. In that moment of connection, you bridge the gap between the human and the cosmic. You are a conscious part of the universe, born from the ashes of long-dead stars, now looking back at itself, pondering its own origins, its workings, and its destiny. You are the universe become self-aware, contemplating another part of itself that is about to undergo a profound metamorphosis. And that is perhaps the most profound legacy of Betelgeuse, not as a celestial time bomb, but as a teacher, a mirror, and a guidepost in our endless, restless quest to understand our place in the grand, beautiful, and awesome cosmos. The universe continues its slow, stately, and violent dance of birth and death, of fusion and fission, of collapse and explosion. And we, for a fleeting instant in the vastness of deep time, are here to bear witness, to understand, and to wonder. Good night.